Okay, so we'll talk about universal hashing, and then we'll talk about BST sort, binary search tree sort in this module. So let us start with the weakness of hash function. Okay, so suppose you have designed a hash function and you want to sell it to the Microsoft, and your friends has designed a hash function and he or she wants to sell it to Microsoft. So the Microsoft open a competition, and so what Microsoft will do, Microsoft will take your hash function and give it to your friend, and your friend hash function give it to you, and asks for find out the input, find out the set where it is performing badly. So find out the set of keys such that it is giving a it is colliding actually for the same slot, for some slot I. So you have if you have time, you can try for all possible key values, and you can find out that where your friend's hash code is colliding for this input. So this is the set. So for this input, it is all are colliding to the ith slot. Okay. So if the hash function is given to you, you can easily come with such a input set, and your friend is also will be doing that. So how to avoid this? To avoid this, we can choose the hash function randomly, so that nobody can come with some input where it will be performing. There will be definitely collision, because this table size is small and this set of keys size is very huge. So there has to be collision, but we cannot find out the set of keys where it is colliding. That is difficult if we choose the hash function randomly. So one way to do that is universal hashing. Suppose this is our a set of all hash function from U to okay, and we call this hash function is universal hash function or universal hashing if among this set we consider the portion which you denoted by bad portion. That means in this portion the function, so bad we defined as such that if you take any key, x y, it will collide. So if the cardinality of this bad portion is cardinality of this by m, then we call this, and then if we choose a hash function randomly from this set, then this is our h, then we call that is a universal hash function, because that will that collision will be less in that case. We can prove that, but is this clear? So this is the bad portion. Bad portion means, so this is a set of all hash function. Among these, bad portion means if we take any two keys, for those hash function which is coming from this bad portion, they will be colliding. So if the bad portion size is 1 by m fraction of the total size, then we will have a then we call this is the universal hash function, and it can be shown that if we choose a hash function randomly from this set, from this universe, then the expected number of collision with x with a key is less than n by m, the load factor. This can be proved. So that means if we choose a key randomly and the expected number of collision with that key is less than load factor. So, it is a good choice if we choose this hash function uniformly at random from this universal of the hash function. Now, we will see an example of a universal hash function, how we can construct a universal hash function. So, construction of one construction, there may be other construction, construction of. So, this is one example of universal hash function. So, what we do? We choose the number of slot as prime, n, let n be a prime, okay, and we decompose the key. So, key is of this form k0, k1 up to k r, and each of these ki's are coming from so we have a big key and we decompose this into, this is the key k0, k1, k2 like this. So, kr. Okay, so, R blocks and each of this part of the keys are ki's are in the range of this. Now, we choose a constant vector a randomly. So, this we choose randomly a0, a1, ar. So, this all the ai's are also less than n, and this is chosen randomly. Okay. So, then we defined a hash function using, so this we denoted by h a of k. This a is the a vector and this is the key, is basically summation of ai ki I is equal to 0 to r and this mod m. Okay. So, this is the construction, or you can take mod and then take the sum, anyway that is same. So, summation, this is the inner product basically, summation of ai ki mod m. So, this is we have a universal of the hash function and we choose a randomly and we generate the hash of that k is like this, summation of ai ki mod m, and it can be shown that this is basically, this set is a universal hash function. So, if we choose a randomly, then it will give a universal hashing. Okay. So, now we will talk about perfect hashing. Okay. So, perfect hashing is what? So, suppose we have given a number of keys is given, this is a static arrangement and we have given number of slot which is basically order of n, and we have to do a static arrangement for these keys, so that when we will search, it should be done in a constant time. So, that searching will be searching in constant time, guaranteed, and this is a static arrangement. So, we are not allowing any insertion or any new keys to be, any new record to be joined or any keys to be deleted. So, this is a static arrangement. So, how we can do that? This is basically a two level hashing. So, this in the worst case guaranteed. So, we should able to search in a constant time, the worst case guaranteed. So, this idea is to do the 2 level hashing. Okay. So, here we have the set of keys which is fixed, we are not allowing any change over here. And so, what we do, we first apply okay. So, this is our 0, 1, 2 up to m minus 1, this is our number of slot. So, we first apply, so these are the keys k 1, k 2, k n. So, we first apply our hash function on it, and we choose the hash function from the universal hash function. So, it will distribute the keys in a uniform way over the slots. Okay. Now, some of the slots will get collision. So, to handle that collision, suppose this slot having 2 keys colliding. So, what we do, in the second level we will use another hash function, another hash table, where if 2 keys are colliding. So, here we will have 4 slot. So, if 2 keys are colliding, so that means we will have 4 slot over here. This is in the second level. So, this is basically and we will have a key value, we will have a is basically coming from that random choice universal hash function, and this 31 is the a, that 31 will decide the second level hash function, and this is basically, suppose we have some key say 14, 27. Okay. So, basically under this hash function, suppose this is the first level hash function h. So, that means h of 14 is equal to h of 27 is equal to 2. This is the in the first level. So, we know 2 keys are colliding here. So, we have a second level hash function with 2 square 4 slots, and there we have to choose a hash function. So, that hash function we are choosing this way, this is our a. So, this is 14. So, this is say 0, 1, 2, 3. So, this is basically 1, 8, 31, 27 is 2, like this. Now, if there is only one, say suppose for this slot, say suppose this is 4, this is 3, 4, 5. Suppose for this slot we have only one. So, there is nothing in this level. So, we have only one element, and suppose for this slot we have 3 elements, 3 keys which are colliding here at 6. So, that means we should have a 9 slot in for the second level hash table, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8, 9 slot, and we need to have a that random for the universal hashing, we need to have a random a which will determine the next level hash function. And suppose these are the number which are colliding here 40, 37, 22 say. So, only 3 elements, but to avoid the second level collision, so we do not want any collision in the level 2. So, that is why we are choosing number of slot is more. If there are 3 elements colliding here. So, we are at the second level, we are choosing 3 squared 9 slot to guarantee that there will be no collision at the second level. So, all this h value, h of 40, h of 37, h of 22, all these are basically 6. They are all colliding in this here under the original hash function. Then we have to choose a hash function for the second level, that is basically h of 86, and for this 41 we have 1 like this. So, this is the second level hashing. So, now when we have to, so this is This way we arrange, this is a static arrangement. So, we are not allowing anybody to join the join the list or join this set or anybody to delete. Now, how the search will be linear time, not linear time, constant time, because if you have to search some key, what we do, we will just go apply the h of this, we will go to the first table and then we will check whether if it is there, we will return, otherwise we will apply once more the second level hash function, and for that we know the hash function because a is given. So, once a is given, then we can construct, we can have h of a, that hash function. So, we will compute that h of a on this and we will go to that table and we will check whether this is there or not. So, this way the time is, the search time is linear, not linear, constant, it is a constant time. So, just 2 times hash function we are applying. Okay. So, now what guarantee us that there will be no collision in the second level is that if this is ith slot, if ni is the number of element which is collating in this level, this is the level 1 hashing, then what we are taking? We are taking ni square now. So, ni is the number of keys collating in the first level at the ith slot, then we are taking ni square. So, here it was 3 keys collating. So, we are taking 9 slot and in 9 slot we are putting the 3 keys. So, the collision chances is, even it can be shown mathematically that the collision is even less than half. Okay. So, now the question is, intuitively it may looks like that we are using so much storage, because for if ni is the number of keys collating in the ith slot, so ni square. So, what is the storage? What is the storage for the second level? Storage is basically, so ni square I is equal to 0 to m minus 1. Okay. So, intuitively it looks like huge, but if you remember the bucket sort where we have the n keys are distributing over some buckets, and there we have this ni's are the number of keys in the ith bucket, and this we have seen, this is basically order of n. So, in the second level we are using this analysis we have done while we talk about bucket sort. So, this is the, so in the second level hashing we are only spending the linear storage. So, overall or if m is also linear, m is, so overall our storage is order of m. So, we are not using the huge storage. Intuitively it is looks like that, but it is not. Okay. So, this is called perfect hashing, which is basically 2 level hashing, and it is showing that the guaranteed worst case search time, and it is basically, and the storage is also reasonably good. Okay. So, next we will talk about binary search tree sort. So, this is all about hashing, up to this is our syllabus. So, next we will go to the move to the next topic, which is binary search tree sort. In short, it is BST. So, what is a binary search tree? It is a binary tree where binary search property means if you take any element x, the key value. So, all the key values in the left subtree is less than x, all the key values in the right subtree is greater than x. So, that property is called binary search property. So, Now, how we can have a sorting algorithm based on the this binary search tree. So, let us have this. So, suppose this is a BST sort, BST sort. So, we have a array of n element and we need to sort it. So, what we do, initially our tree is empty and then we will slowly insert the element into the tree, we will form the BST. So, sorry, 1 to n, we will just do the tree insert, BST insert, we will see how this code is, and then after that we will perform a in order tree walk, then it will give us a sorted. Perform an in order tree walk of T. Okay. So, for example, suppose we have this tree, suppose we have given this 3, 1, 8, 2, 6, 7, 5. So, suppose this is our array, this is our element we need to sort. So, first tree is empty, we need to form the tree. So, this is the tree insert. So, 3, then 1 is less than 3, we will put it here, this is the tree insert 8, and then 2 is less than 3, which is greater than 1, 6 is greater than this, but less than 8. So, 6 is here, 7 is greater than this, less than this, greater than this, and then 5 is greater than this, less than this, 5. So, this is after this BST insert. Now, we need to perform this in order traversal, we need to traverse the tree. So, for that in order traversal means we first visit the left, then root, then the right. This is a recursive call, left subtree, root and right. So, if you do that, so left, then again recursively, so it will basically give us 1, 2, 3, then again for this part 5, 6, 7, 8 sorted. Okay. So, this is what is called BST sort. Now, we need to analyze this code, how much time we are, so what is the run time for this code. So, what is the run time for in order traversal? This will take linear time, order of n, because this is just we are visiting each of this node. Now, the question is what is the run time for this? So, this will be time for this sorting, because this is the major time. So, well, this will depend on the tree, on the numbers. Now, suppose our tree is like this, suppose our input is already sorted. So, that means our tree will be like this, and then what is the run time, what is the time to insert this? This is basically depth of the node, and this is basically 1 plus 2 plus up to n. So, this is n into order of n square, this is the worst case. Now, when is the best case? If the tree is like this, so this is the worst case, then the runtime is order of n square. Now, if the tree is like this, very good tree, I love to draw this tree. Anyway, so this is what is called balanced tree. So, now if the tree is like this, then what is the runtime? What is this tree insert? Tree insert is basically n into, so order of n log n. Okay, because there are n by 2 nodes over here. So, for these nodes each time is log n. So, for that it is order of n log n. So, this is the best, this is the lucky case. So, can you remember some sorting algorithm we know which will give us this runtime? Worst case is n square. This is, yeah, that is the Quicksort. So, we want to see how this Quicksort is related with the BST sort. So, for that let us just take one example. Suppose we have 3, 1, 8, 2. Suppose we want to sort this using Quicksort and we choose this as a pivot element. So, if we do that, if we apply the partition, then it will partition into 2 parts, 1, 2 over here, and then remaining over here 8, 6, 7, 5, and here we are assuming that we are ordering are not changing. So, this is some sort of stable partition we can have. So, ordering are not changing, the same ordering they are achieving here. So, all the elements here are less than x, all the elements here are greater than x. So, again we choose this as a pivot. So, this will be 2, and again we choose this as a pivot. So, it will partition like this. So, this is all the elements 6, 7, 5, and again we choose this as a pivot. So, 5, 7 like this. So, this is just the Quicksort partition, this is the Quicksort, and then if we just draw this, if we just draw this, okay. So, this is, if we remember the form of that we already done the BST sort for this example, and we have the same tree. So, that means same number of comparison we need for Quicksort and the BST sort, I mean to get the BST tree in maybe some different order, because same number of comparison 3, everybody has to compare with 3. So, there also when we insert, when we make the tree, everybody has to compare. So, same number of comparison is required for both the cases. So, that means runtime for Quicksort is same as runtime for BST sort. This is a good observation. So, this observation we will use when we talk about randomized version of BST sort, randomized BST sort. So, what we do? We have given the array, we just randomly permute these numbers. We apply some random permutation on A, random permutation on A array, and then we perform the BST sort. Okay. So, we have some numbers, we are randomly permuting this number, and then we will perform the BST sort, and in that case, so this is similar to the randomized version of Quicksort. So, the runtime for this is runtime for randomized BST sort is same as runtime for randomized Quicksort. So, the expected runtime for randomized BST sort is same as expected runtime for this. So, expected runtime we know n log n. So, from here we can show that expected height, this is the things we want to achieve, expected height of this tree, height of randomized BST tree, BST is basically log n. So, expected height is log n. So, that means if we have some numbers and if we just do the random permutation on this number, then it will give us the balanced tree expected. So, it will be log n height tree. So, very nice tree, balanced tree, but this is expected, there is no guarantee, but we can say the expected runtime, expected height of this tree is log n. Thank you.